Hello and welcome dear learners, students, professionals and viewers. Welcome to the another informative topic on dissolution testing, cross-linking and enzymes used. This is part 1. In this part 1 we will understand the cross-linking, the reasons for cross-linking and what are the probable points to overcome the cross-linking and how the enzymes are used for this dissolution testing for the cross-linked formulations or cross-linking in gelatin capsule shells or gelatin coated tablets. So let's start with the video. First is gelatin. See, gelatin has a wide use in the hard gelatin capsule shells, and also sometimes the gelatin is used for coating the tablet formulations. So the gelatin is basically a protein, and it is extracted from the skins and bones, cartilages and tendons of the animals. We all know that it is a protein obtained by either partial acid hydrolysis or base hydrolysis or alkaline hydrolysis of the animal collagen. So when there is a acid hydrolysis, the gelatin obtained is called as type A gelatin, or when there is a alkaline hydrolysis or base treated hydrolysis, it is called as type B gelatin. So gelatin is a soluble protein and it dissolves in the warm water. Gelatin is used as a main component for making the hard gelatin capsule shells. It is also used as a binder and coating agent in the pharmaceutical formulations. Gelatin is used to make hard gelatin capsules, and gelatin is used to make soft gelatin capsules also. So mainly the gelatin is used to make the capsule shells. Either it is hard gelatin capsule or it is a ribbon of the soft gelatin capsule. So this is the basic structure of the gelatin. It is a protein. Then coming to the problems with gelatin. So there are many advantages of the gelatin, like its availability, its compatibility with the formulation, the manufacturability and stability. And along with those, there are some problems, and the biggest problem is cross-linking. Now what is the meaning of cross-linking? See, cross-linking is the formation of covalent bonds between the gelatin polymeric chains, and these covalent bonds are strong chemical linkages. So the cross-linking is a irreversible process, or cross-linking is not a reversible process. That means once the bond is formed, the bond will not break, as it is a strong covalent bond between the gelatin polymeric chains. And the impact of this bonding or cross-linking is that the soluble gelatin converts into the insoluble one, and due to this insoluble gelatin, the disintegration time gets increased, and due to this increase in the disintegration time, dissolution rate becomes slow, and sometimes in the hard gelatin capsules and soft gelatin capsules, the dissolution may fail, and that is due to this cross linking. So the cross linking is always a variable process. The dissolution becomes variable due to the variability in the cross linking. So you cannot predict that the batch to batch uniformity will be there in cross linking, or unit to unit variability, unit to unit similarity will be there. Due to cross linking, the unit to unit variability will be there, batch to batch variability will be there. So the dissolutions become variable. Now coming to the exact understanding on the covalent bonds. So the covalent bonds are this. Here you can see that this is a interstrand cross linking. See, here it is the polypeptide backbone of the gelatin, and here one bond is there from one strand to another strand, that is inter-strand cross-linking between the two polypeptide backbones. Also intra-strand cross-linking will be there. So this is intra-strand cross-linking, and due to this cross-linking the gelatin becomes insoluble and there is a failure in the dissolution of hard gelatin capsules, soft gelatin capsules or gelatin coated tablets. Now the sites are shown here. Site number 1, site number 1 here, site number 2 here, here site number 2 is given, here site number 1 and site number 2. So the site number 1 is possible peptide bond seizure by pepsin. So here the pepsin will break this bond and it will make the gelatin soluble, or it will make the dissolution faster. Then another enzyme here shown is pancreatin. Pancreatin, site number 2 here, it will break the chains. So this is the information about intra-strand cross-linking and inter-strand cross-linking in the gelatin polypeptide backbone. And this cross-linking renders the gelatin insoluble, and that's why the dissolution failures come. Then what are the factors affecting cross-linking? Why this cross-linking happens? So this cross-linking happens due to heat, high humidity, sometimes light, and also the variation in the heat and humidity will have impact on the cross-linking. Heat may also enhance the aldehyde formation, and this aldehyde formation will lead to the cross-linking. So these are the storage conditions. Then coming to the formulation front, API and excipients. Generally APIs with carbonyl groups shows the impact on cross-linking. If the capsule contains APIs with carbonyl groups, then there will be a chances of cross-linking. Then aldehydes in the excipients. Example is starch. Then polyethylene glycol. Polyethylene glycol auto-oxidize to form aldehydes, and these aldehydes increase the chances of cross-linking. Any other sources like aldehydes are there, then metal ions and sugars are there. Rayon coil in packaging may also lead to cross-linking, and the exposure of the formulation to formaldehyde will lead to cross-linking. So these are the main parameters or factors which impact the cross-linking. Now how the cross-linking is identified? See, cross-linking is also called as pellicle formation. The another word is there, pellicle formation. So you can observe it visually. If your dissolution fails for the capsule formulation with gelatin, which may be soft gelatin or hard gelatin capsule or gelatin coated tablet, by visual observation in the dissolution bowl, you can observe the formation of membrane or swelled cotton-like membrane will be there, like this. This is the pellicle of capsule, and this is the pellicle formation, or it is cross-linking. So by observation of the membrane which is swelled and insoluble gelatin mass or pellicle formation, so due to this the delayed capsule opening will be there and dissolution will be slower. So pellicles can be identified by visual observation. There are some instrumental techniques also which involves instrumental testing of NMR, DSC, FTIR, which can detect the cross-linking in the gelatin molecule. Then capsule switching. If you perform the dissolution with capsules and you observe this cross-linking, so empty the content of the capsule, fill it to the fresh capsule shells which are not loaded on stability, empty capsule shells which will be fresh, and perform dissolution. If the observation is different in both the batches, that means with normal stability sample of gelatin or old gelatin capsule shells batch and the new one, so test the capsules and observe cross-linking or slower dissolution, empty the capsule content and fill in the new capsule shells or fresh capsule shells and observe it. Then you will get to know whether the cross-linking is there or not. Then what are the possible ways to have the dissolution in place with the cross-link capsules? So generally the cross-linking, and due to cross-linking the dissolution failure is not considered as a significant change, as the USP, EP and JP provides a recommendation or recommends the use of enzymes for the cross-link formulations. The USP General Chapter 711 dissolution allows the inclusion of enzymes in the dissolution medium where gelatin capsules experience dissolution failure. Hard or soft uh, gelatin capsules and gelatin coated tablet that do not conform to the dissolution specification, repeat the test as follows. Where water or a medium with pH of less than 6.8 is specified as the medium, the individual monograph, the same medium specified may be used with the addition of purified pepsin that result in the activity of 750,000 units or less per 1000 ml, that is per liter. So if the pH of the medium is less than 6.8, then use pepsin. For media with pH of 6.8 or greater, pancreatin may be added to produce not more than 1750 USP units of protease activity per 1000 ml, that is 1 liter. Now with the stimuli article, the limit is increased up to 2000 units. European Pharmacopoeia also allows for the use of enzymes with justification and proper method development in place. The Japanese Pharmacopoeia does not accept addition of enzymes to overcome the cross-link. So JP is not allowing the enzymes use. JP recommends the use of succinated gelatin to avoid the cross-linking in gelatin capsule shells. So this is the type of gelatin which will not lead to cross-linking. Then coming to the enzymes that are present in the body. Why this pharmacopoeia recommends the use of enzymes and why the regulatory authorities don't consider the dissolution failure due to cross-linking? Because these enzymes are the proteins which are essential for digestion. In the stomach, pepsin is the main digestive enzyme. Pepsin is secreted by the stomach. Pancreatic enzymes are secreted by the pancreas. The function of these enzymes is to break down the food. Pepsin and pancreatin break down the proteins. See, the enzymes are there in the body, bile salts are there in the body, that means in the GIT. So the cross-link formulation will not show much more impact in vivo. That's why these enzymes are used. So the enzymes can be used in the dissolution media. Coming to the second part of enzymes used, pepsin, papain, bromelain and pancreatin are there. So based on the pH of the medium, these enzymes are used. Why? Because the pH affects the activity of the enzymes. For pepsin, maximum activity is at pH 2 and it is used in acidic pH. Pepsin is stable over the pH range of 1.1 to 6. Above pH 6, pepsin rapidly irreversibly inactivated. That's why it is used at the acidic site. That means when the medium is acidic. At pH 8, pepsin is completely deactivated and the units recommended are not more than 750,000 units per liter. Then coming to the papain. Papain comes from papaya. It is extracted from the papaya. Optimal pH is around 5 for the gelatin as substrate. See, the optimal pH will change as per the substrate, but for gelatin it is pH 5 and not more than 550,000 units or less per 100 ml, that is per liter, is recommended. The protease activity, that is the limit of this pancreatin enzyme, is given as per the pharmacopoeias and the regulatory authorities is with protease activity of not more than 2000 units per 1000 ml, that is per liter. Then coming to the another part, that is significant change formulation stability. Now if there is a cross-linking due to this gelatin shells or gelatin content, and if the dissolution failure is there on stability, then will that dissolution failure will be considered as a significant change and the batch will fail? So the answer is no. Significant change due to dissolution failure due to cross-linking in hard gelatin capsule shells or soft gelatin capsule shells will not be considered as a significant change, because mostly cross-linking does not affect the in vivo behavior, as most of the times the capsule will open in vivo as the enzymes and bile salt are present in vivo in the GIT. The capsule opens and release the contents in vivo, but in extreme cases it may have impact. But that is in the only extreme cases that can be treated as a case by case basis. Generally, cross-linking does not affect the bioavailability. Based on the above facts, the dissolution failure due to cross-linking is not considered as a significant change, and that's why the dissolution method with enzymes can be developed and justified. So here I have taken some examples of soft gelatin capsule and hard gelatin capsule. So midostaurin capsule is there and enzalutamide capsule is there as a soft gelatin capsule, and celecoxib capsules are there. So here you can see for midostaurin, the deionized water with 0.5% polysorbate 20 is there, and if cross-linking is there and if dissolution fails, then tier 2 medium will be there, that is deionized water with 0.5% polysorbate 20 containing pepsin. Similarly, for enzalutamide soft gelatin capsules, the medium contains CTAB as a surfactant in 0.1 normal HCl, and in tier 2 it will contain the same amount of the surfactant with 600,000 USP units of pepsin. Then coming to the celecoxib, in tier 2 750 ml of simulated gastric fluid will be there, which includes the pepsin, and after 20 minutes while stirring, add 180 ml of appropriate concentration of SLS solution for final concentration of 1% SLS. Add about 70 ml of 1.2 normal NaOH to adjust the pH to 12. So in this example, the pre-treatment is there. The pre-treatment topic will be covered in the second part of this video series, and also in that video we will discuss the method development with enzymes, pre-treatment options and best practices for dissolution testing, so that the cross-linking can be avoided, and if there is a cross-linking, then the method should be there in place to have the proper dissolution of the cross-linked samples. Here we have understood what is cross-linking, why this happens, what is the impact of cross-linking onto the formulation and dissolution or drug release, whether the dissolution failure due to cross-linking is considered as a significant change or not, what are the various enzymes used for cross-link samples, and how these enzymes are selected based on the media pH. So thanks for watching the video. I hope you might have got a good understanding of this video. So please do like, share and subscribe to Pharma Learning in Depth channel. And please note that the dissolution related questions are always asked into the interviews. For making this video, I have referred USP, EP and USFD Orange Book. Also, I have referred the literature available on dissolutiontech.com. Thank you.